Is there any part of this week that's like we're at home and we're doing something? I think I heard someone say it's like, what's that called when you're
Asynchronous.
Do we have asynchronous?
I don't think so, but it's coming up the STAR test day.
Is that what it's next week?
I think it's next week.
I'm actually not Eastern.
I think it's next week.
I think you can come over the summer.
I want to say it's like the 22nd or something like that.
I said.
I kind of like that.
I don't think you need a taste. How do you like you did that? It was really nice. What is that? University of Bacon Albert. University of Vermont. What's the
Vermont. Oh, it does fit.
The A for Albert.
Someone laughed.
It's for Virginia. There's like Vermont.
Two letters.
But then Virginia makes it very clear that it's
Oh.
Vienna.
Or should have gone to Vermont. I don't know anything. That was a big assumption.
Where's he going instead?
I think University of Vermont. That's the upstate. Yeah, Vermont was the.
Yeah. Vermont. But in the winter, when you're actually there at school, it's like
Negative 100 degrees.
In where, Vermont?
It is negative 100, like south.
It would be very cold.
It's legit negative.
It's really nice in the summer though.
I used to go to camp in New Hampshire. It's very nice. They don't even have AC. During the year.
That'd be nice.
Is that Wesley?
All right, guys, we are very close to finishing. We have 35 total lessons. Today we're doing number 30. So we'll do 30, 31, 32 this week, and then 33, 34, 35 next week. And then we'll be done. And then the following week, we'll have our last test. It's towards the very end. I want to say it's like the last day of April or pretty close to it. Or at least, I guess, the last school day of April. I don't remember exactly what day, but it's during that following week. Then we'll start our final project, which the final project, you'll pick a topic and you'll pick a group to work with on that topic. And so it's got kind of a lot of leeway with how you want to do that. And then that'll be it. We'll be done. So problem set from last week is due Thursday of this week, which we don't have class Thursday. You will have your afternoon classes Thursday. So if you'd rather finish it Wednesday, you can do that. But I just decided to give you guys an extra day. Then the next problem set, it's only over today and tomorrow. It's a 2 lesson problem set that'll be due on Tuesday of next week. So again, as that test kind of comes closer, they're going to get a little closer together. But I think the last few are just 2 lessons, 2 lessons, 2 lessons. All right, so a lot of our kind of final lessons are going to kind of touch on some simple applications of some of the stuff that we've learned. So we're not going to go very in depth into any of these applications, but most of them you could do entire, fields of study. You can almost major in some of this stuff and really, really study it. We'll just spend like a lesson a piece on them. So we'll obviously do very simple examples. And just to kind of give you an idea of where you might see some of this stuff come up if you were to study any of these fields in college. So first one is called graphs and networks. Oops. As we do our project once we start our project, you'll see that really there are ways to use matrices in lots of different fields. probably more so than calculus. Calculus is very physics, engineering oriented and isn't used super extensively in a lot of other places. Matrices are, because matrices are ways to keep track of large amounts of data and do stuff to large amounts of data. And that pretty much exists in most fields in one way or another. So once we start doing the project, which again, you're going to kind of have some choices on, you can kind of find stuff for matrices in a lot of fields. With our graphs and networks, what we're basically analyzing is pathways between locations. And those could be very physical, like the Königsberg Bridge problem, which is a bunch of islands connected by bridges. And so you can analyze ways to get from one island to another and the different pathways that can get you there. Or they could be a little bit less physical, like radio waves being transmitted, or electricity moving along circuits, or whatever. It doesn't really matter. It's anything that kind of would travel from one place to another, and you're kind of wanting to analyze the pathways of getting from one place to the other. So in the Königsberg Bridge problem, you basically have these different land masses in a town. And so, you have the one up here, you have one in the middle, you have one down here, we have one over here. And then you're just looking at the different ways to get from one place to the other. And there's all these bridges that kind of connect. And so to get to that middle island from the top, you could go on this bridge, or technically you could go, on this bridge over here and then across, or even down over here and then across, or then across this way, or whatever. So you'd have all these different pathways that you could follow. So then we'll separate them into two different things. Nodes are basically the location. So in this case, the nodes would be the land masses. And then the edges would represent the pathways. And so we wouldn't really draw a full picture. We would draw what we call a graph, which is not really a graph like you're used to in like algebra, but a graph is just kind of a simple version of nodes and edges. So on this particular one, I would draw the 4 different land masses that we have. And then your edges would just be very simple lines or curves, kind of showing that I have connections, 2 bridges on connecting each of those land masses, one connecting to here, one connecting to here, one connecting to here. Okay, and so we would simplify the picture as much as possible, just showing all the different ways I could get from one place to the other, those places being the 4 nodes, or basically points on this graph. And then the simple curves would represent pathways to get from one place to the other. And again, advanced graph theory is like an entire field of study of it in and of itself, but these can be applied to lots of different jobs and things like that. One, kind of on a civil engineering standpoint, is transportation. If you're trying to look at roads and which roads need to be larger, which places need more roads to get in between because the current roads are overtaxed or whatever, or new traffic signals that are needed, ways to reduce traffic, save money, things like that. Airline companies probably have the best visual way of seeing this. So if you look like in the back of an in-flight magazine or even on the website, they'll show kind of all the cities that they travel to, and then they'll have kind of the paths, of the plane going from one city to the other, and the hubs will have tons of these things coming out, and then each of those might have little paths going to closer regional cities or whatever that they connect. And an airline company would have people that analyze, like, where do we need new direct flights to open, because there's lots of people traveling between these specific cities that maybe have some industry in common and people are traveling a lot, or maybe people aren't traveling on this certain flight that we offer currently, and maybe we could get the few people that are to go on not nonstop flights, so that we're saving money and not doing this nonstop flights between cities that people aren't even flying on. So they would have people that kind of analyze that, trying to figure out where would we open new flights, where would we close flights that aren't really being used, and divert those through smaller towns or something where you'd fly there and then to wherever you're going. Or computer chips and circuitry. Basically, everyone's trying to make things faster and smaller all the time. And so chips are getting smaller and smaller and smaller and more efficient, and you're trying to figure out how do I make those pathways efficient and small and stuff like that. So you could think of these as the paths on a circuit board as well. Okay, so we'll make our graphs very simple as possible. So you'll basically have a certain number of nodes and a certain number of pathways or edges. And so if I have 4 nodes, I would literally just kind of put my 4 nodes on the page. You kind of can put them wherever you want. Generally, we try to arrange them in a way where very few edges cross other edges to keep it from being too confusing. But you can kind of put them wherever you want. So I'm going to put 1, 2, 3, and 4. And then you could just put your edges on there. So I have an edge from 1 to 2. And so our edges will be directed, meaning they have a direction to them. It's going from one place to another. So typically, if you were doing graph theory, you would probably have, if you wanted it two-way, you'd actually have a second path that would be directed the other direction, as opposed to one that's a kind of a two-way path. We're not going to do any of those. All of ours are going to be one-way, one-path connections, because that creates another level of complexity that we're not really going to go into. So we're going to have these simple kind of one-way paths. So we have 1 from 1 to 3. We have 1 from 1 to 4. 1 from 2 to 4. 1 from 2 to 3. And 1 from 3 to 4. Okay, and so we'd have a simple picture. And again, yours might look a little bit different. You might have labeled the points differently, which would make the picture come out a little bit differently. It shouldn't really matter as long as you're consistent throughout your whole problem. And then we're generally going to want to label the edges as well. And again, it doesn't really matter which edge is which. I think I just did them in the order that it was given here. So 1 to 2, 1 to 3, 1 to 4, 2 to 4, 2 to 3, and then 3 to 4, edge 6. Don't have the room to write it there. Okay, and again, the only reason that you really even need the label is because as we do anything mathematically to the graph, we just want to know in the edges that we have after mathematically altering stuff, what kind of the new ones corresponded to in the original. So it doesn't really matter which one you call edge 1, 2, 3, 4, 5, 6. You just need to know which ones are 1, 2, 3, 4, 5, 6. So that then after doing an altering, I will have a new 1, 2, 3, 4, 5, 6. And I kind of want to know which corresponded to what. So just keep it consistent throughout your problem. Okay, and so I drew it a little bit nicer here. So we have edge 1, 2, 3, 4, 5, 6. We have our nodes 1, 2, 3, 4. And from this, we create what's called an incidence matrix. So in our matrix, our columns correspond to nodes. So here we have 4 nodes, so we'll have 4 columns. And you don't typically have to put a 1, 2, 3, 4 up there, but we'll have 4 of them. And then our rows are going to correspond to edges. So since we have 6 edges, we'll have 6 rows. And then these matrices are very simple. Basically, I would look at every edge and figure out what nodes are connected, which ones are not. So like edge number 1 connects node 1 and 2. So 3 and 4 will have zeros because they aren't connected by edge 1. And then everywhere else you'll have either a 1 or a negative 1. A negative 1 on the node that you're coming from and a positive 1 on the node that you're going to. So edge 1 is coming from 1 to 2. So I have a -1 under the first column and a 1 under the second column, basically signifying I'm coming from node 1 to node 2. I don't connect node 3 or 4 with that edge. Okay, and so edge 2 comes from 1 to 3. So I'd go from 1, give me a -1, to 3. So I'd put a 1 in the third column. And then it doesn't connect 2 and 4. So I'd put zeros there. Edge 3 comes from 1 to 4. Edge 4 comes from 2 to 4. Edge 5 comes from 2 to 3. And then edge 6 comes from 3 to 4. So every row should have 1, 1, 1, -1, and then everything else is a bunch of zeros. So it should be a pretty simple matrix made of just ones and zeros and -1s. And really every row just has 1, -1, 1, +1. Because every row is just going to be one edge that connects one node to one other node. And again, your rows may be in a different order if you called the edges different things in a different order. It doesn't really matter. It's just that once I do something to this matrix, your edges will correspond to whatever you first called edge 1, 2, 3, 4, 5, 6. Okay, so this is called an incidence matrix. It'll be M by N. M is the number of edges. Okay, so same number of rows as you have edges. N is the number of nodes. So you'll have the same number of nodes as you have columns. And again, just have ones, zeros, and -1s. The ones go on the node where the edge is heading. The -1 goes on the node where the edge is coming from. And then all the non-connected nodes by that edge have zeros. So it should be pretty simple little matrix. Okay, so another example, we'll do another 4. I think most of the homework ones are 4. Most of the examples are 4. So we'll do those same 4 nodes, but we'll have different paths. So I have a path from 1 to 3. And I'll just go ahead and call that edge 1. I have one from 3 to 2. I'll call that, edge 2. One from 2 to 4. And then one from 1 to 4. Yeah, if there was ever a 3 to 1, that would be a different edge. Okay, but we're not going to do that. But yes, normally you could make it more complex by having different directions and stuff. Okay, here I would have a 4 by 4 since I have 4 edges, 4 nodes. Edge 1 goes from 1 to 3. Edge 2 goes from 3 to 2. Edge 3 goes from 2 to 4. And then edge 4 goes from 1 to 4. Okay, and there's your incidence matrix, there's your graph. Okay, for us, we're only gonna ever have one path, at most one path connecting any 2 nodes. You might not even have a path. So notice like node 1 and 2 are not directly connected here. Neither are 3 and 4. So at most, we're only gonna connect one path between any 2 nodes. So we have kind of our 2 extremes would be one that's called complete, meaning every pair of nodes is connected directly by an edge. So our first example was a complete graph. Okay, every single pair is connected directly together. and that would be called complete. Okay, and you'll have what we call closed loops when it's complete, meaning like, ignoring the direction, there's enclosed, polygons here, like that would be a little enclosed loop there, or an enclosed loop there, for example. Okay, it would be have enclosed parts. A tree is a graph with no closed loops. It's basically the smallest number of paths to connect them all, at least indirectly. So something like this would be a tree. Okay, every node is connected, just not necessarily directly connected.
Oh, like a tree. I get it. Like it always called that. Nice. The branches in the tree are. You know what I mean?
Because a branch doesn't typically attach to the tree in two different places.
Yeah.
Okay, so this would have no closed loops, right? It would basically be, if you unfolded it, just a straight line. But this would kind of be the smallest graph we would have, would be a tree. You're typically not going to have a node just sitting out unconnected, because then that's not really part of the system. So we would ignore it. Like if nothing is interacting with that node, we would not really include it in our analysis that we're doing. So the smallest we'd have is a tree, where they're technically all connected, just not directly connected to each other here. But there is some path from 1 to 4. It's just that it has to go through the other nodes to get there. And again, some of them you might be going backwards against the traffic flow, but there is some path there. Okay, so maximum number of edges. So basically, to get a complete graph, you would take 1/2 the number of nodes times the number of nodes minus 1. So we've been using 4. So if we would do 1/2 of 4 times 3 and get 6, that's the maximum number of edges needed to connect every node to every other node directly. The minimum number to actually be at least indirectly connected, in this case, would be 4 minus 1. That was our tree, needed 3 edges to connect all 4 nodes together, at least by an indirect path. So you could have something in between, right? We could have 4 edges or 5 edges as well. But complete is going to be kind of that maximum number. A tree would be that minimum number, and then anything in between, you'll have some closed loops and some that aren't necessarily closed loops. It's like we did that one up here. This is neither complete nor a tree. Okay, there is a closed loop, but every node is not connected directly to every other one. 1 is not connected to 2, and 3 is not connected to 4. So we have 4 edges here. We're somewhere between complete, 6 edges, tree, 3 edges. All right. If we do elimination on our incidence matrix, what we would do is we'd be reduced to a tree. So you basically reduce to the smallest number of paths. If you just started adding and subtracting rows and trying to get kind of your U matrix that we did for a long time, what you'll end up with is everything will stay connected, but you will lose all your closed loops. Your closed loops represent dependent rows. So like when I look at, again, kind of that one we had at the beginning, if I look at the incidence matrix and I look at these 3 rows that make up these 3 edges, they are dependent. Since they form a closed loop, I know that the 3 rows that represent those 3 edges are dependent. If I look at like this one, and this one, I would know those were independent. Because they don't form a closed loop, it means those are 3 independent rows. Again, the edges are rows. So if we just look at this edge here and this edge here, this edge here, they would be independent because they aren't a closed loop. So if I do elimination, remember that we're basically, when we're doing elimination, we're eliminating all of the kind of dependent rows. You would end up with just a tree. Okay, they would all stay connected, but they would all stay connected by the smallest number of paths possible. All right. We've already said this could basically represent all sorts of things: current, water, traffic, oil, whatever, things flowing from one place to another. Our kind of final examples here are going to be voltages. So it's kind of an electrical engineering application. Again, very simple. So if we start looking at what we've been doing, AX equals B. Okay, in an electrical setting, this could represent voltage being applied at the node. So our X's could be voltages. And then when we multiply, we would get differences in voltage, right? Since we have all those rows with a 1, 1, and 1, -1 in them, when I multiply row 1 times those X's, I'll get X2 minus X1. And then for row 2, I'll get X3 minus X1. And then X3 minus X2, and then X4 minus X1, X4 minus X2, X4 minus X3. But if I were to multiply that all out, because of having a 1 and a -1 and a bunch of other zeros, all you're going to get is a bunch of differences in voltage. So AX here would represent difference in voltage. If I said AX equals B, B would be the differences themselves. So it's like I'd be trying to find what voltages would I apply to get these differences. Okay, and I could put a B there to do that. So we start looking at all the things we've done to this situation. So we did a bunch of stuff all semester, a lot of times with no context, just like here's a matrix. What's the null space? What's the row space? What's all this stuff? So say we take this one, and what do we find when we look for its null space? So again, null space is just when AX equals 0, which means if AX's differences in voltages, a null space would be when are those differences all 0? Okay, so you'd be looking for, when what was my matrix? -1, 1, 0, 0, -1, 0, 1, 0, 0, -1, 1, 0, -1, 0, 0, 1, 0, -1, 0, 1, and 0, 0, -1, 1. Okay, so I'd be looking for what makes, oops, this is 0. So we could look mathematically, not having any clue what we're looking for. We could find the null space. And what you would find is just look at every row and think, what would I multiply that row by to get 0? So the first row, right, as long as the first two numbers were the same, it doesn't matter what the second two are because they'd be multiplied by 0. In the next one, as long as the first and third were the same, it wouldn't matter what the other two were because they're being multiplied by 0. In the fourth row, as long as the first and fourth numbers were the same, right? We'd basically be looking for all the voltages applied at the nodes. As long as they're all the same, the differences will all be 0, right? Logically, that should make sense. If all I'm getting is a difference in voltage, as long as I apply the same voltage everywhere, the differences will be 0. So my null space will always be the basis. Will always just be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 for these specific incidence matrices. No matter kind of the size, you'll just have a bunch of 1s there. Okay, because think of what you have in your rows. You have 1, 1, 1, -1, a bunch of zeros. As long as those numbers you're multiplying by are the same, you'll have a positive one of those things and a negative one of those things, and then a bunch of zeros. And you add them together, you're going to get 0. So null space would represent where you want the voltages all to be 0. I mean, the differences, sorry, to all to be 0. Okay, also, if you put zeros in there, you get 0. Okay, row space is the linear combination of the rows. So our dimension is the rank of the matrix. Okay, which is just 4 minus the dimension of the null space here. Or 6 minus the dimension of the left null space, but we haven't talked about the left null space. So we just looked at the null space. Basis had one vector in it, which means it's one dimensional. Which means the rank of our matrix will be 3. Again, with these matrices, the dimension of the null space will always be 1 because the basis will always be 1, 1, 1, 1, 1, however many ones you need in a vector. So our rank will always be kind of n minus 1. So in this case, it'll be 3. And so for our basis, we'd be looking for 3 independent rows. Which we could use what we've been using to find 3 independent rows. You could do elimination and look for independent rows or whatever. Or look at your graph and pick 3 edges that don't form a closed loop. In your incidence matrix, those 3 rows are independent. So if I look at my graph and I have like edge 1, 2, and 3 or whatever, don't make a closed loop, well then those 3 would be independent and they would be a basis for the row space. They're not the only one. That you could choose some other combination, but you'd be looking for 3 paths that don't form a closed loop. That would be a basis for the row space. Okay, column space is the linear combination of the columns. Okay, it'll still be a rank 3. So the dimension will be 3. Remember, the row space and column space have the same dimension. So in this particular one, it would be still be 3. Okay, which means we could choose any 3 independent columns. We'll have 4 columns. So any 3 of them will be independent in this case. And that'll always be true because it's basically always going to be n minus 1 is our dimension. So with column space, n minus 1 of them, you just choose that many. So if there's 5 columns, any 4 of them are independent. If there's 7 columns, any 6 of them would be independent. You could also, again, use what we've done to figure that out. But all we're looking for is that, a multiple of 1 plus a multiple of the other, multiple of the other. We're looking for 3 columns where I could take a multiple and get 0 only when all of those are 0, not 0, just a 0. There is no other combination to get 0. Remember, that's the definition of independent. But we have all sorts of ways we could figure that out other than that. Okay, and remember the columns kind of represent the nodes themselves. So when we're looking at the columns and trying to analyze the columns, we're looking at the nodes, what's happening at the nodes. If we're looking at the rows, we're looking at what's happening on the edges. All right, Kirchhoff's voltage law is that the components of AX should add to 0 around every loop. So here where I had a bunch of closed loops, I'm just going to look at one for right now, but 1, 2, 4. Okay, we had more closed loops than that, but from 1, 2, and 4, that made a closed loop. We had an edge going from 1 to 2. Edge 1 did. We had an edge going from 2 to 4. That was edge 5, I think. And then we had one going from 1 to 4. That was edge 4. So this is edge 1, 4, 5. Okay, around every closed loop, we should see those components add up to 0, which notice that they will here. So edge 1, x2 minus x1, plus edge 5, x4 minus x2, Notice if we go around, okay, if we go 1 to 2, 2 to 4, 4 to 1, we're going backwards. That would indicate a subtraction rather than an added. If we're going to try and go against the flow, that would be minus edge 4. And notice if we were to simplify that all down, we have an x2 minus an x2. We have an x4 minus an x4, and then we have a negative x1 minus a negative x1. This is all going to be 0. So what that means is if we're going to try and set this equal to b, okay, and find some differences, what voltages would I apply to get these differences over here? This is telling me that B1 plus B5 minus B4 must be 0. Remember that when, again, on the first test, when we were looking for what types of B's have a solution in AX equals B, in these, it must be where closed in loops are giving you 0. Okay, that's the only way that you could get a solution. This one, this is not the only constraint. We'd have to look at all the closed loops. So we have, we have a closed loop in our original graph here as well, and here as well, and really the whole thing. All the ones that are kind of enclosed, we would have to kind of verify that the B's added up there in every single closed loop would be 0. And again, if you're ever going against kind of against the flow or direction, those would be subtracted. Okay, and then when we look at like the left null space, remember you're just transposing A. So our edges would now be the columns and our nodes would now be the rows. And so now we'd be looking down each node instead of each edge and seeing what makes that multiply to 0. Here we'd be basically looking down node 1 and multiplying, and we'd have like negative y1 minus y2 minus y4 equals 0, and y1 minus y3 minus y5 equals 0, and so on. Just take the rows times those y's and add it to 0. What this is basically giving us is Kirchhoff's current law, that the flow in and out of every node should be 0. So as we were to kind of pick what's happening here as what's flowing in and out of each node, which here we would see like in node 1, everything's flowing out of it, right? -1, -1, -1. There are no positive ones. So this would not be a great example of trying to solve this, because the only way that's possible is if that's all 0. Okay, the only way everything could be flowing out, and you need to figure out where that's 0, that's only going to happen where what's coming out is 0, if there's nothing coming back in. You're looking for flow in to equal flow out at each node. So like, again, this one I just made up, so it's not a great example, because if we look like at node 1, everything's leaving. So flow in can only equal flow out if all the things leaving are 0, then sure. But then that's going to impact what happens everywhere else, right? You go to node 2, what was flowing out of 1 had to be 0, which means the only thing flowing into 2 is also 0. So what would be having to flow out of it is 0. So this isn't a great example, because normally you'd want some in and some out, and you're going to find kind of the balance of what's happening there. It's like you'd have something like, if you'd looked at 2 here, what's flowing in would have to equal what's flowing out here. So like you'd want to balance there. So that's Kirchhoff's current law, which is basically looking at the left null space. You're looking for the places where that would balance out. And basically kind of trying to compare the edges coming in and the edges going out, and making sure that there is a net of 0 there. All right, all the examples are probably pretty simple. The homework here should be fairly simple. This is a huge field of study, but that's about as far as we're going to go. So if you guys have any questions, let me know. If you don't, you guys have a good rest of your day and I'll see you guys tomorrow.